Okay. Alright, so that's obviously not a terribly interesting one. I need more light in here, just a second. Let's turn on this light. Let's get some music, actually. Okay, so 3, 2, stack min. Oh, I was reading this one last night. I was not sure at all how to do this. How would you design an how would you design excuse me. How would you design a stack which in addition to push and pop has a function min which returns the minimum element? Push, pop, and min should all operate in O of 1 time. Um, so the min one, I'm really not sure how to do that. Uh, so, alright. Probably copy. Well, let's just write a new one. Chapter 3, Problem 2, stack min. Yeah. Stupid. Oh, you know, something I was going to try today was getting Enter to work. Do I have Enter installed? I think I do. Oh, I don't. Okay, well, I'll deal with that tomorrow-ish then. Okay. Anyway, it's fine. I can just tab back and forth. It's just a bit silly. Or maybe I'll do it during lunch. We'll see. Okay, so this was our big failure from yesterday. But we're going to do stack min, right? Today. And so that's just going to be a... I guess this creates a stack, right? So presumably it could create a stack and also take elements, initial elements, right? And then we're going to do a bunch of tests on it, but okay. Boy, they're asking for a lot on this one. All right. So we want to push a pop and a min function on this guy. Push. So push takes an element. And pop takes a nothing. And min, I guess, also takes nothing. Alright. So, we're building a stack. Cool. What is a stack? Well, in Clojure, actually, a vector, I think, entirely matches what a stack is, right? So a vector has a pop, has a push in the form of conj, or into, or many other things, yeah. Has a peak, definitely. It literally has a, well, it doesn't literally. Anyway, there is a peak, there is a pop, there is a push equivalent, and there is also there is no is empty, but you can just take the count on a stack, and on a vector, I mean to say, and if it's 0, then it's empty, if they really, well. So, I guess, yeah, let's just implement is empty too, just to be like in line with their definition of a. Let's actually, yeah. So push pop min is empty. Wait, what's the third thing that's part of a stack in general? Push pop is empty, and peak and peak. I mean, implementing peak is almost dumb because it's just going to call peak. But anyway, all right. So our stack when we actually, I mean, I'm going to call it stack min, but yeah, our stack is literally just a, well, so if it was just a stack, right? If it was just a stack, if this function was stack and not stack min, right? I would literally just take the, you know, uh, the items of vector. Whoops. So put items into vector, and that's it, basically. Or actually, that's dumb. Why am I doing that? Just vec on the items, right? But it's slightly more complicated than that because we also want this is min thing, right? Or we want the minimum item on the stack. And I mean, having read the next chapter, I can say that to hold something that holds the minimum, a min heap comes to mind, you know? But with a stack, I mean, we could also concurrently maintain a min heap maybe, but then we also got to figure out things like when we remove an item from the stack, we need to also remove the item from the min heap. And then furthermore, the min heap, even as good as the min heap is I think in log n or log of n. Yeah, I think it's log of n, right? In terms of insertions and deletions. So, so yeah, that clearly kind of breaks the whole stack semantics, which are fundamentally constant, right? I mean, pushing and popping off a stack should be constant. Assuming a dynamic stack, it should be constant, amortized, right? And I'm wondering if that's what this question is really asking. Is asking you to recognize the fact that the min is usually an amortized cost. And so, although occasionally you will linearly have to scan the stack to find the min when you happen to pop something off that is the min, the great majority of the time you can just return the min, right? And yeah, I mean they're so okay. Let's think about this. Yeah. So rather than just having a vector, I guess I instead am going to have a map that contains my stack, which is a vector of items, but also contains my min, which is the min of items, right? So to create the stack took a linear amount of time because I mean, for two reasons. I had to run through every item here, and B, I had to run through every item here. Apply the min of items, right? Let's talk about peaking. So peaking is pretty simple. You just peak off the. I guess all these guys are going to take an argument because they're functional, right? So. And stack. Let's just check that are actually streaming properly. Twitch. Oops. Okay, can I hear anything? Uh-oh. There's no volume because... Okay, yeah. Seems to be working. Alright. Alright. So, each of them takes a stack as an argument, and sometimes they take an additional argument. Well, they'll actually only push those, really. But... I see that their definition of pop is to... Yeah, it's a bit weird, right? Like peak and pop are both... Peak is fine because peak doesn't expect to change the value. But pop it's kind of not fine because, you know, the question is, do you want to modify the stack or do you want to modify... Yeah, I think pop is actually... Is pop supposed to return a node when you do that, or is it just supposed to... No, it's not. Okay, so actually pop's definition does agree. Pop should return a new stack. Yeah, okay. So, or it matches the definition in the closure row. So some of the 3 of these are just pretty easy. We're just going to update. So if it was just the stack, all we'd literally have to call is peak on the stack, right? But it's actually not. It's the min stack, right? Is that what we called it? Stack? Is it min stack or stack min? It's stack min, unfortunately. Okay, well, stack min, yeah. Stack min, stack min, stack min. So it's a special type of stack, right? I have half a mind to put this min thing in the metadata, then I don't need a map and all this kind of stuff. Let's just give it a shot and see how it feels. Maybe it's wrong. Yeah. So let's use the metadata. And metadata on any item that is a collection type, I believe, you can put metadata into the item, right? And this will be it'll be shared across, right? So the metadata, if you do a modifying operation on the metadata, on a collection type with metadata, the thing that you modified into will also have the same metadata. The interesting thing though is the metadata does not factor into equality, right? So 2 objects that are value-wise equal but have different metadata will still be equal. So now we can kind of simplify a little bit of the code, because now we really are just from the outside point of view, we're just talking about a stack, right? But we're talking about a stack that has some metadata underneath it, right? Where it specifically has the min, right? Apply min on items, right? And the only person who really cares about this is the min, right? Well, that's not true. That's the guy who gets it, right? So how does this guy get the metadata? Well, he takes the stack min. He takes the stack min, then he gets the metadata on the stack min, and then he gets the min of the stack min, right? And that's the min. So that is definitely a constant cost, right? What about peak? Well, peak is pretty simple. You just call peak on the stack min. And this is why I kind of wanted to use the metadata, so that we can just treat it like a vector, that happens to have some metadata that's of interest. Peak does not modify anything and does not affect anything, so we don't need to worry about the metadata. IsEmpty is similar. We can just say empty stack min. Very easy. Push and pop are going to be a little more complicated, because they will have to modify. They may have to modify the stack min, right? So I think it's the case that so here's a question: does the stack min always? So the stack is not sorted, right? But we do know that we've been keeping track of this the entire time. We can rely that pop has always put the metadata, the collection's min, the collection's metadata's min, as the minimum element. So we can trust that that's true. That whatever we have in this location, right, is in fact the min element. Which means things like when we pop an element off, and the element we just popped off happened to also be the min. That's actually, yeah, here's a question. Should we actually record the min, or should we record the index of the min item? If we record the min itself, then we're basically saying, hey, whenever you pop an item off that happens to be the same as the min, then that means you need to rescan through the stack, right, the remaining stack, and find the min item now. There's a bit of shortcut there that you don't linearly have to scan the entire thing, because you could be. I think I'm gonna keep the min. I think the min index might have a performance advantage, but I think I'm gonna stick with the min, because if you rescan through the entire thing and you ever find one that is equal to you, right? Then that was equal to your previous min in the remaining stack, then then you're done, right? There's nothing lower than that because you would have marked that as the min. So okay, I think that makes some sense. So let's talk about let's talk about keys. And let's grab the min out of the meta of the stack min, right? So we now know what the min is. Ooh, I should have named that. I'm just going to call it minimum, right? Because I don't want to confuse it with the actual function name. Minimum. How come that? Oh, because one's a keyword, one's a symbol. Okay, so that's the actual minimum. And okay, if we know what the minimum is, so now that we know what the minimum is, we're going to peek at stack min, right? V. We're going to. I mean, I guess there's no reason to. But yeah, we can use our own peek that we've written here. We're going to peek at stack min. That's going to give us a value, right? And then we're going to ask if v is equal to minimum, right? Then if that's the case, we got to do some special stuff. But if that's not the case, right, then all we just need to do is return the pop of stack min, right? Actually, in both cases, we're going to return the pop of stack min. So maybe in all, well, no. In both cases, we're going to return the pop of stack min. In all cases, we're going to return the pop min. That's what pop does. But in one case, we're just going to leave the metadata alone, right? If v is not equal to the minimum, then we're just going to leave the metadata alone, right? We're just going to put the metadata on here. Actually, it does feel a little bit silly, because I feel like if you're doing this, just return the pop of stack min. I don't know, pop of stack min, right? But if you aren't doing this, you're going to have to actually build a new metadata, which is also going to be the pop of. I think I like this format better, even though it's a bit weird the way it's done. Sorry, this one better, I mean to say. So this one just returns either you were a perfect match, or either you're not actually popping the minimum, so it doesn't matter, in which case just return the metadata, or you are popping the minimum, in which case we need to calculate what the new minimum is. Now the simple way to do that. Oh, we should actually keep this out here so that we can new stack min, right? So we can just do it like this, but also so that we can call min on new stack min, right? This is a linear cost. Technically, we could make that slightly better by stopping when we find one that matches the existing minimum, but that's only reduces a linear to a linear. It does save stuff in reality, but probably saves about half on average, I guess, of the traversals, but it doesn't actually make a big difference. So if v minimum, apply min, new stack min, m. Okay. Actually, let me just look at what it looks like the other way, because I just feel weird about making a new object when there's really no need. But so if v is equal to minimum, so if that's not the case, then we're just going to return new stack min. But if that is the case, we're going to return something like this and this. I don't know. I kind of think kind of think this is a little clearer, actually. Yeah, new stack min. Yeah, I kind of think this is a little bit clearer. So this is pop, right? It's going to, when you pop and you happen to have popped something off that is the minimum, it's going to be a linear. Now that, see, this can't, I mean, I'm saying it is, but it's not really, because for instance, if I put all the same value onto the stack, I put all ones onto the stack, it is going to linearly run through, every single pop has a linear cost, you know? And that kind of violates the constraint on the stacks that stacks have constant cost, you know? Now, if I did do the thing I was talking about doing, where rather than doing this, we instead actually just, you know, filter on values that are less than or equal to our current value and stop when we get something, well, that nothing will be less than our current value, but something may be equal to our current value, right? Or sorry, greater than or equal is what I meant to say, right? We filter on things that are greater than or equal to our current value in the stack, and we stop when we hit something that, and we stop taking it for the first one we get, you know? Oh, not the first one. We stop taking it as long as it's not equal, you know? Or we stop taking it when we run into something equal. That would reduce. That's interesting. Does that actually matter? Let's write a little function called findMin, because I think we're going to maybe need it for push too, but I'm not sure. No, push is actually easy to find the min, because you just compare your current min to the thing you're pushing on, and that's it. Yeah. But let's write a little function for findMin within a stack. Within any stack, right? It's not a min stack, but just within a stack. And I guess technically speaking, if we're going to be like that, then this is also just takes a stack. It doesn't really take a stack min. And this also just takes a stack. It doesn't really take a stack min. In fact, all they actually take is collections, but we're talking about stacks here. So findMin takes a stack and what was I doing? Oh yeah. Alright, so it takes a stack and also returns or runs across the stack, filtering on things. Oh, it does need to know current min. Yeah, so filters where the current, where the value is less than or equal to the current min, right? And we're saying take while the value is not equal to the current min, right? What's the advantage of this versus the previous one? Or versus just the apply min new stack, and then we take the first on that. So let's think about this. We take the stack, right? We're filtering on all the items where the value of the item, this is backwards, isn't it? The value of the item, the current min is less than or equal to the value of the item. So every item that has a value that is less than or equal to the current item. So it could be the same value somewhere deeper in the stack, or it could be a value that is greater than the current value, right? And yeah, we got to take more than just that, don't we? We can't just take the first, but anyway, then we're going to stop if we actually found something that is equal to the current min, right? And then we're just going to call our apply min on that, right? I think that makes sense, right? Because the nice thing about this is it'll short circuit. It'll short circuit, but I'm not sure whether it'll include the actual one we want. Take while. Yeah, I don't think it will. I think it'll stop right before the current one. That's not what we want. This is why I was not excited about doing this, and I just wanted to do this. I'm going to leave it for now because we can just worry about an optimization later, but I feel like there's a find min that is a little bit better than this, and that would actually handle the pathological case of having a stack where every item is the same, you know, or the value on the stacks are all the same. Because this one, what we want is ultimately something that short circuits if the value that is found is the same, you know. Yeah, I'm pretty sure take while would stop at right before the one you want to take. Returns lazy equals successive items from collection while predicate items return logical true. Yeah, so that would not include the one that actually, so negative. If you got -2, -1, but you don't include the one that actually does match it. Is there like a drop and tell or something? This is the same thing. Just returns the lazy sequence of the items in collection starting from the first item for which predicate returns logical false. Drop all negative. So it drops all the negative ones and then starts returning the positive ones. That's cool. But I just want something that only... split with some... Yeah. Where's the cheat? Here you go, quick ref. Nope, that's not what I was looking for. How do we get to the cheat sheet quickly? Okay, so we want a sequence thing. We got take while, we got drop while. I mean, I guess rather than doing like this, we could just do it in multiple steps, right? So wait a minute, is this backwards? For the current min. Well, no, now because we know that whatever we just popped off is at minimum going to be equal to the current min and maybe greater than the current min. Okay, or we should call this the old min. Yeah. But, okay, so let's just focus on splitting it up simply. New mins, right? This is a filter, so it's lots of candidates. But this is a lazy sequence, so it shouldn't process all of them. I shouldn't process any of them until we actually evaluate it. But then we can have an equal mins, right? Which is going to be the same thing, but a filter on the filter, right? On old mins. It's not on old min, it's on stack. But an equal mins, which filter on the filter. Is your are you equal to old min, right? And still nothing has been processed. And then I'm just going to say if empty, which I'm pretty sure we checked yesterday, actually evaluates as seek not, right? So it actually has a constant cost no matter the size of the collection. If empty equal mins, right? So if we know there's nothing in equal mins, then we also know that which is, I mean, it's not to say that that's cheap, you know, because effectively you're paying a linear cost to do equal mins, right? Right. If this is true, then you're paying the minimal cost to get the equal mins. But if it's false, you're paying the linear cost to run through all of equal mins, and then you're paying another linear cost, I think, to run through new mins again. I think. Although new mins has been evaluated by somebody else, but has it? Yeah, I'm not clear about that. So you can either if equal mins is empty, then you can just take the first of new mins, right? Or no, sorry, you can take the apply plus of new mins, right? But if equal mins is not empty, then you can just return old min as the new min, right? So yeah, I mean the great majority of, I mean, assuming there is now a new min, right? Then the problem is this guy actually requires a full linear scan to really say that it is empty. Right? So you're kind of already paying a full linear scan every time you run find min anyway. So I don't know if this actually gives us anything over just doing this, you know? If you're already paying for, I mean, this is a full linear scan, right? But you're already paying for a full linear scan by doing this. But actually, right, I think the thing we're really missing here isn't so much that whether this is a full linear scan or not. It's the, yeah, it doesn't really matter. I think this whole thing is just a bit of a, this is a sideshow. Yeah, this is, but is because the savings here, the amortized cost, isn't the scan itself. The amortized cost is the fact that this is only going to occur rarely, hopefully. Well, no, it will occur in most situations. In a normal situation, no, it would occur rarely. But the problem is in the pathological situation, it would occur constantly. You know. Wait a minute. No, equal mins. So, but yeah, so the only thing it's not a sideshow because the only thing we're trying to fix here is the pathological case of every single item being the same value in the stack, and so having to literally min every single item in the stack every time you pop, right? The pathological case is the problematic case. But if we do this, I mean, so new mins is a lazy sequence that will return only the items where you are greater than or equal to the old min, and then equal mins is a filter on that one. It says, okay, of those, only give me the ones where it's actually equal, you know? And so if you're empty, wait a minute, maybe we should just ask if you have a first. Right? Because if you have a first, then we just return the new min, right? But if you don't have a first, then the only thing we can do is basically figure out what your new minimum is from. Now let me think about that. But now what have we done? Now we've made it so that, all right, if you have a first, that means we'll return you the first item that actually is equal, you know? So in the event that we did find an item equal, there was a savings there, right? In fact, in the pathological case, we're going to return the first item off the stack, right? Which is indeed cheap, right? But in the worst case scenario, which is where you don't have an item that is equal, right, at all, we do still need to basically go through the entire stack and find the entire stack, all the items in the stack that are, oh, you know what, this is entirely unnecessary. Because we already know that nothing in the stack, everything in the stack is greater than or equal to you. So this is just, I'm pretty sure this is just entirely unnecessary. So just take it off the stack, right? Equal mins are all the items that are equal to you. Yeah. New mins, you're going to ask, is there anything in here, you know? If there is, that's the new min, you know? It's a bit weird. And then we return the new min. The new min is going to actually be also the old min. Yeah, I feel weird about doing this if let thing now with that. I'm just going to say if empty. I'm really going to say if first, right? If first equal min. So now, if there's anything in equal mins, right? If there's anything in equal mins, then we just can return the old min, right? Because that means, oh, there's another guy in there that also matches this value, which this handles the pathological case of having a stack full of the same value, right? This now returns in constant time when you do that. Otherwise, if there's nothing in the stack that's equal, what we got to do is basically scan through the entire stack and just find the new mins, basically. It's kind of actually not stack. It's really the new stack and the old min, right? Right. So just to sort of. So I think that makes sense, and I think that this. I think this kind of handles the pathological case of having all ones in a stack, right? Boy, I feel like I'm doing this entirely wrong because I'm not sure these problems should take this long. All right, and then finally push, right? Let's get to push. So push is a little bit simpler in that you're basically going to pull the same thing as here, right? You're going to pull the new stack data. Oops. You're going to pull the new stack data, or the minimum data, and you're just going to pull the new stack data, and you're going to just with metadata. No need to preserve stuff or be clever here. You're going to conj onto the stack min the value v as the value, and the metadata is just going to be the minimum of the min of minimum and v, right? Yeah, we could have preserved this by using the if thing here again. Oh, let's just match the pattern to make it to make reading the code a little easier. So new stack min is just going to be the conj of stack min and v, right? So that's going to be true for everybody. But now it's basically an identical pattern of this. But if you are equal to the minimum, then actually now that I look at that, I kind of like the other one better. Yeah, whatever. This is literally 3 lines. Let's do this one. It's a bit silly since you're literally creating a new map every single time you conj onto your stack, which you could get away with not doing that if in the event that your minimum is equal to the value you're putting on there. You could just use this map rather than create a new one, but who cares? That doesn't even matter. So yeah, I think that's push. Push is pretty simple actually. You just compare the current minimum you have, and you're just literally finding the new minimum. Not even really, just whatever it is, put the min into minimum, and conj onto the stack, and that's it. So push is pretty easy. Min is easy. Oops, except it's actually minimum now. Peak is easy. Is empty is easy. pop is a little more complicated, and but I think it may have an amortized cost of constant. It's not, it's not always constant, but it may have an amortized cost of constant. In that, let's run through the code again. Segment is also easy in that you're just building a stack, and literally just put the items into a vector, and give it some metadata, which is, yeah, the linear of all the items. Trying to think of this puts them in the order you would expect. I would expect to see if I have stack min 1, 2, 3, 4, 5. What do I expect? Do I expect the stack to contain from root to top a stack 1, 2, 3, 4, 5 or 5, 4, 3, 2, 1? I don't like this. Let's not do this. Let's just do items, right? And then I'm almost thinking just don't do items, because then it's like ambiguous which way you mean it, So I'm kind of just thinking do this. Start at 0, Oh, that's a good question. What is your minimum if you have no items? Nil, I guess. I do not want to do with this. So that is something we need to deal with on min, right? I feel like that's appropriate. The minimum should return nil. Is it? There's no mention of like. No. So there's actually no. I mean, like the only way to truly indicate that this is. Oh, this makes it just much more complicated. Okay. If minimum is nil, as in nobody has specified the minimum, then we need to not. Where are we using this? Okay, so this would be false, which means we just use the new stack min. That is incorrect. This would be false. So I feel like now we have to say if there is a minimum and the minimum is equal to the thing you're popping off, right? Then build the metadata. But this guy doesn't build the metadata, but that's because he has on the assumption that we already had correct metadata there. Ugh. Yeah, if you're popping the first item, there's like a special case. Okay, I don't want to thread my logic through all this thing, so I'm gonna deal with some predicate here, but if stack min count is 1, right? Then it's just with meta. Back up. I don't like this. Okay. If right, if you're popping something off, you can only pop off something that is. You can only pop off the empty stack. Actually, that's a question. Should you return an exception if you pop? I kind of feel like you should. Yeah. Okay. There. And push, so that you can't pop off the empty stack. You can't peek off the empty stack. Actually, no, I feel like you should be able to peek, and that should just return nil. But of course, you don't know whether that nil means that nil is put on the stack, or whether... So I think that's the only... you can is empty an empty stack. You can min on... Can't really min on an empty stack either. Okay. And you can push onto an empty stack. So really this actually says that but if you do push onto the empty stack, it does... I think you can do this. So basically saying if there was no minimum in your metadata, there was no minimum, like right here, right? Then let's put a minimum in there. Alright, so now your minimum is either it's gonna either be the actual value of minimum, or it's gonna be the value of 0. No, it's not 0. I need a number that's smaller than any number that could exist. Or I just need separate conditions. Oh dear. Alright. Am I just doing something wrong? It's just way too complicated. Is empty peek min push find min. And pop. I feel pretty good about this. This is saying in an empty stack there is no minimum, and there is no item in the stack, obviously. Pushing. These guys I think are fine, right? And they should all, yeah, just work. There's no conditionals in them. This guy was fine, except there may not always be a minimum. If there is no minimum, I can't take the min. I can only take the, I mean, it just, if there is a minimum, then I can take the min of the minimum and v. But if there's not a minimum, then I just gotta take v. You know, that is the minimum now. Right? That's pushing onto the stack. So now we've gone from being an initial stack that had no minimum, like literally did not have the key, to a stack that now has a minimum, which is just v. Okay. Now to reverse that, what if I want to go from the state that has 1 item to the state that has 0 items? Okay, but do I always need to do this? Yeah, I always do need to pull. I mean, if we've gotten past this point, we know that we can pop, right? it may be the case they're about to pop the last item off the stack, but we can pop, right? So that means we do have a minimum, because everything that has a positive number of items on the stack should have a minimum. And, okay, so that I think this one's good for every path. This one is asking what is the thing we're going to peek off. That's fine. This one is asking, let's build the new stack itself. That's fine, right? But then I guess there's actually a cond here. And we're saying first of all, if the stack min count is equal to 1, right? Then we're doing one thing, which is we're building the new, actually no, wait, if the new stack min, right, the thing we just built is equal to, we don't need this at all. If the new stack is just 0, right? Then that is, we just popped the last item off the list. Then that's fine, but now we're going to have a with meta of new stack min. And we're going to go back to the empty metadata, right? Because we have no minimum now. However, if the minimum is this, if we are equal to the minimum, then we do need to find a new minimum. So we take the new stack min, and then we calculate the new minimum, which actually we're not applying this, we're just doing it. Otherwise, otherwise that means we're not going from 1 to 0, right? Because we would have exited here. We're not replacing the existing minimum. We're not popping something that is the existing minimum, so we can skip by here. And we are just returning the stack, So that means our minimum is still fine, and we just return the new stack. And let me just make sure that's how cond works, because I feel like there maybe you have to put else in there or something like that. All right. Yeah, you got to put just a thing that would always end up being true. So else new stack min. That's a complicated pop, but I think it may have an amortized cost of. So great majority, like if you're doing 1, 2, 3, 4, 5. I feel like a lot of things have amortized cost of. Actually, yeah, this doesn't help me. This does help with the pathological case of having the same values, but if you have an incrementing values on the stack, yeah, this isn't gonna help. If you have incrementing values in the stack like 1, 2, 3, 4, 5, your min and that is the 5 is at the bottom of the stack and the 1 is at the top, right? You had 1, right? But you have to really scan through 2, 3, 4, 5 to know that 2 is the smallest one. You can't just assume that 2 is the smallest one. Can we just use 2 stacks? I mean, does that make any sense? I mean, if you use 2 stacks, that means push could have a linear cost, right? If I use 2 stacks and I'm putting things in reverse numeric order, like 5, 4, 3, 2, 1, I put in 5. Well, there's nothing to scan. That's fine. I put in 4. Well, we got to scan past the 5. Or we got to scan up to the 5 to know to push the 4 on top of the 5. I put in 3. Well, we got to scan to the 4. So that's actually the good case if I put it in 5, 4, 3, 2, 1. What if I put it in 1, 2, 3, 4, 5? I put in 1. I'm trying to maintain a ordered stack, right? I put in 1. There's nothing in there, so 1 goes on top of the stack. I put in 2. Well, I got to scan past the 1 to put in 2. I put in 3. I got to scan past the 1 and the 2 to put in 3. I just put in 4. I got to scan past the 1, 2, and the put in 4. I gotta scan past the 1, then the 2, then the 3, then put the 4, and then put the 3, then the 2, and the 1 back on top of the stack. All of them have a pathological case that is linear, which is not surprising because we're dealing with the stack. But so I really don't think this helps anything. I think we might as well just do apply plus min. Apply min everything, you know? But yeah, this actually does take 2 arguments, so the old min was the minimum. But yeah, I don't actually know how to do this. How can I do constant min lookup? Okay, and let's relax it a little bit. How can I do amortize constant min lookup? This new one, I think with a find min, you know, there may be bugs, but as I envision it, would be able to short circuit in the event that any values are equal. It'll just take constant time to find the next one, right? But that's only for equals. For anything where the value is greater, it does still need to scan through all of them, right? So if you do enter things in sequential order, I think, where the 1 is at the top and 5 is at the bottom, if I pop off the 1, now I gotta, you know, I because there is no more 1 on the stack, I still need to scan through 2, 3, 4, 5 to find the new minimum. That is not an amortized cost of 1. Let's think about other data structures. Does a hash map help me with this somehow? Does a yeah, I don't know. I don't have a good one here, you know. New stack old min, yeah. How do we do this? I mean, I feel like it's a fairly decent implementation. I mean, like, I feel like there's cheats here where I could just use an ordered like set, right? Is that not a sorted set? I mean to say. Oh, and that's actually a sorted set of okay, so I think maybe we want a sorted map, probably. We can do that. Use of a source. Okay. So that's sorted map. Okay. Where was I? Here. What is sorted map by? Okay, so it just lets you specify your comparator, which could let you do, for instance, a reverse sorted map, right, with a max rather than a min. Okay, but yeah, it is sorting on the keys. So you could use a sorted map, and the map would keep the ordering, and you could just put the or the map would keep the ordering, right? And if you just take the first off the map, the first item you get will always be the lowest key, and so that'll be the min item, and you could use I guess the index position in the vector as the values, right? A set of values. So a map with the key of the actual value and the values on the map would be a set containing the index position that has that value, you know? And so your basic job would be to remove, when you pop off, you would remove the item at that index position. And so I think that, I mean, this is how I would actually do it in reality. But I feel like, without the addition of sorted map and all that kind of stuff, how would you do this just using stacks, or just using the data structures that we should be aware of at this point, which are stacks and queues, hash maps, like how do you keep something in ordered sequence other than with a min heap that is not a linear cost, I mean, it doesn't matter. I need better than linear. I need a constant cost for this. Yeah, I'm just not clear about that, honestly. Well, okay, I guess it's time to look at the hints, right? So, first hint is number 27, stack min. Actually, first let me think about, maybe it's because I'm doing it in an immutable data structure that something's just not obvious here, but I'm looking at the actual code that they do it with a node, right? Or with nodes and all that kind of stuff. Is there some clever thing you could do with nodes to know what the minimum stack is? What the minimum item in the stack is? I mean, so basically, you at the my stack level have a top, and you have those four functions that I have too: the pop, the peek, the push, and the isEmpty. Those deal with a node, one node at a time, and they all kind of start by starting from the top, right? Yeah, so... Oh, and they throw exceptions in their peek as well, for instance. And also in their pop, if you pop onto... Or if you try to pop off an empty stack. And they don't... No, they throw exceptions on peek and on pop, and they do not throw exception. Well, there's nothing to throw on push, and there's nothing to throw on isEmpty, and that's similar to what we have here. And there's also nothing that they don't have it in the code example of min, but I assume the same rule applies on min. You can't take the min in the same sense that you can't take the peek of an empty. But man, oh man, I just don't see how you can do how you can do constant lookup of the min on a stack. Yeah, okay, it's time to look at the hint. Yeah. I was kind of thinking previously that I was going to just try to do the problems without looking at hints, and then look at hints after I've done all the problems, because but I don't know, maybe I should start just looking at the hints at the end of the prompt for all the problems anyway, just to see if I missed something that was really clever. I think I may start doing that, actually. But the purpose is really to learn new things, not to affirm that you can do old things. So, number 27. Observe that the minimum element doesn't change very often. Yes, that is it only changes when a smaller element is added or when the smallest element is popped. Okay, I think I have observed that. Thank you. What's the next hint? The next hint is... where am I? Number 59. Okay, well, let's before being just flippant about it, let's just observe. Have we really observed this? Yes, that is a principal observation, I think, of this thing, is that, this should ideally only occur... These two cases, this case can only occur 1 out of n times, right? This case can occur... There's pathological cases where it would occur all the time, but in general it would occur fairly rarely, in a randomly distributed set of numbers, it would occur extremely rarely. Well, no, it would occur. That's a good question. I don't actually know what the distribution on that is. I think is it 1 over n times? How can that be this? This can only occur at one point in the entire application, or in the entire stack's life cycle, which is when you're about to pop off when you did just pop off the last item, right? This can occur, but it's fine too, because it also has a constant cost to doing this one. This one can occur, what are the odds if I'm randomly emitting numbers, right, that the number I emit is smaller than all the previously emitted numbers? So for the first number, obviously the odds are 100%. For the second number, I feel like the odds are 50% that it's higher and 50% that it's lower. For the third number, is it a quarter? Is it a third? I'm not sure, but it gets faster. It gets smaller fast. It may be either 2 to the n, or I'm not really sure, but it occurs rarer and rarer, right? The more items you have in the stack, the less likely you are to make a minimum that is less than the stack. I get that. And then the great majority of the time, you're just doing this one, which is just a constant cost one, right? You're just popping off the stack, and you still have the same min. So I do totally get that. My problem is in the pathological cases of either being fully ascending, fully descending, or fully the same value, I feel like these are really bad. This fully the same value is really bad, right? Because, well, in the naive way, or in the original way, where I just said apply min stack, that means every single time the value is the same, it has to scan through the entire stack. My attempt here was to reduce the number of scans it had to go through by saying, hey, if you actually found the next item and it is the same, there's more than one item with that min in the stack, then just, all right, just let's move on, same old min. Oh, you know what, this is supposed to be, oops, I lost my place. I need to get some of those bookmark things. All right, so same old min, but you do actually need to put this in a map. Minimum. Okay. But it's got pathological cases that are literally linear, right? That are linear every single time. The worst one, the worst one is the. Do I need 3 separate cases and 3 separate strategies for handling the minimum? Is that like I need one for everything's ascending, one's for everything's descending, but how do I know that everything's ascending? And one for everything's equal? I think this one efficiently handles the everything is equal one, right? This, this officially handles you are not the same, and so we need to update us. This particular function, find min, handles the everything is equal case, right? Or there is an equal case. It especially well handles the everything is equal case, because it'll only scan the next item on the stack and then stop, and then we're done, But it still is a linear cost if everything is not equal, as in we need to find a new minimum, And so, okay, so let's say we can walk beyond the everything is equal case. I still feel like in both the ascending and descending case, so wait, if we're ascending, then if we're doing 1, 2, 3, 4, 5, where 1 is at the top of the stack and 5 is at the bottom, then that's the case that we need to handle. If we're doing 5, 4, 3, 2, 1, then we actually have no cause to handle anything, because 1 is at the bottom, and so our min is never going to change until we get to the very bottom of the stack. So that's a good one. The descending one is a good one. But there's still the ascending case, I feel, where it's like 1, 2, 3, 4, 5. I have to scan through the entire thing to know what the next item is, or what the next min is, right? And that will, it will not equal, right? And so this will not be true. And so we will end up doing this linear scan every single time. So I think the only case this doesn't handle efficiently is the ascending case, right? But I'm just not clear how to get around that, honestly, I mean, there definitely appears to be a pathological case here where it's terrible performance, it's going to have to do a scan on every single pop. Okay, all right, so I am acknowledging it. I am stating that I'm not sure what to do about that, and I am looking at the solution. Or I'm looking at the hints, I mean to say. God, I need to get some, bookmarks or something. This is ridiculous. This book is gigantic. 27. All right, so we looked at 27, and it told us something we were pretty much aware of. Look at 59. Well, maybe I can put this thing here to keep up to this page. Look at 59. And 59 says, what if we kept track of extra data at each stack node? What sort of data might make it easier to solve the problem? Okay, so I was kind of looking into that when I said, can we look into the node? But does that help? What extra data can we keep track of here? Now that's interesting. What if I had the way they're doing it, where it's not just a list, really, or it's not a vector. It's instead a literal bunch of nodes. I mean, oh, wait, maybe. So my first thought was, what if the nodes contained a pointer to not the next node on the stack, but also a pointer to the next lowest value in the nodes that are their successors. But I'm also thinking, wait a minute. What if each node, because it's a stack, we know the order, right? I mean, what's dumb? Because it's a stack, it's always taken on and taken off in a specific order, right? And so at that level of the stack, we knew what the min was at every level of the stack, actually, right? It's only, this is a bit embarrassing because I should have thought of this because I should be used to using immutable data structures, right? But there's no reason. I gotta look something up because I just realized there's something I kind of don't know about my own data structures. This is a bit we're just gonna comment out this whole thing, but I'm just curious if okay, so let's sort of say I start with conj of a vector, and that's it, Oops, that's not what I meant to do. Huh? That's no. Chapter 3, problem 2. Okay, so we have the empty vector, right? All right, but then I'm going to say, okay, conj of this, and with meta, conj of this, and we're going to say a is equal to 1, And it'll still print out the same way, but then if I ask for the metadata of it, okay, a equals 1. That's weird. You get a line number? I wonder. That's odd. Huh. I've never seen that before. A's 1, line 54. Weird. That's the first. I am not sure what's going on there. But anyway, you got your A1, right? But then if I pop off that. Do I still have the metadata? Oh, I thought it wasn't empty. Oh, you're right. It is. It is. Okay, so I actually put data in my vector. Well, no, I don't. And then what I'm going to do is I'm going to conj onto this guy, right? Another thing. I'm going to conj the value 1 on, right? So let's just confirm that that's... First of all, if I just conj the value 1, do I still have the same metadata? That is not what I meant to write. Yeah, I do have the same metadata, right? So metadata transfers across operations on the collection. And just to, but what if I then did with meta, that whole thing, and then, I'm going to do b is equal to 2, right? I would expect to see b equals 2, yeah. But then, if I pop off of that, will I go back to a equals 1, or will I go to b equals 2? In terms of the metadata, I will stay on the b equals 2. So it doesn't... All the operations preserve the existing metadata. They don't back themselves back up into the previously existent metadata when you last did the operation. Okay, I kind of think I knew that, but I wasn't really sure. Okay, so metadata is just, it's kind of sticky in a word, in that once you set, whatever you set in whatever the collection's current metadata is, any operation you do on that collection is going to preserve the existing metadata. Interesting to know, or interesting to concretize, or whatever the word is. Alright, so this is obviously, I feel, I should stop worrying about how long I'm taking on this, it doesn't matter. Okay, so, Emacs. And so, alright, if we can, we can't preserve the metadata, but what we can do is we can maintain at each stack level, we can maintain what is the min heap, or what is the min at that level, right? Because all we need to ask for that level is what was the min at the previous level plus what is the min at the previous level plus plus our new min, right? Take the min of our, the new value plus the previous minimum. God damn, I keep saying plus. Take the min of the new value that we're popping in and the previous min, and that is the new min at that level. Okay, so I could do this with the metadata now, but now I just feel like this is just getting ridiculously confusing. And so instead, I think what I'm going to do is just... I hate to throw all this away, but I really don't think a lot of it's very useful. So I almost want to get rid of the metadata concept as a whole, like it's not playing out well. In fact, I think that's probably one of the principal issues here is that I'm sort of manipulating the metadata through time and relying on the sticky property of the metadata. But let's just deal with the stack, and let's just rather than putting, So yeah, now our stack is, when you create a stack, you just create a stack. It's very simple. But when you push and pop a stack, let's just keep these as code examples, but we'll create new ones basically. I don't think we're going to need this anymore, honestly. So let's also comment this one out, right? And then let's just use defen push. We're going to take the stack min, right? And we're also going to take a value that we want to push. Defen pop, and we're going to take the stack min, and that's it, And I think these functions are still the same, although actually no, this isn't. Stack min peak minimum, right? Can you call peak on something that is the empty stack? I don't know. Yeah, you can. It's okay with that. I'm I mean, because they did exceptions on their nodes, I'm going to do exceptions on my nodes, right? Assertions right here. So you can't peek on an empty stack. You can't min on an empty stack. You can't call it as empty on an empty stack, obviously, because otherwise it wouldn't have a lot of purpose. But I guess is empty isn't really necessary. So you could just peek, and if you get the exception, then you know you can't peek, or you know it's empty. But anyhow. Alright, so we sort of commented all of this out. And we're going to restart our thought process here. When you create a new stack, you're just creating an empty vector in reality. When you push, what we're going to do is we're going to take the peak. We're going to take, we don't really care about your value, but we do care about your minimum, right? Minimum, right? And on the peak, and that's going to call into my peak, which I think is okay, right? Oh, you know what's cool about that is actually we don't have to write the assertion here, right? Because we can rely on the assertion occurring in the peak. So anyway, but we're going to peek on our stack min, right? That should return the last item. Ooh, no, but we are actually going to need to modify this a bit. Because this shouldn't return, this doesn't currently return a value, this returns, and now it really does need to be a stack min. Okay. But, because it's going to return stack min, oh, you know what this, I don't want to override this. I'm going to call it peaker, just to keep the thing from conflicting, right? Stack min, peak, and then I'm going to call, we need the metadata, right? So we need the value, right? So basically, what is the thought here? Every item on the stack is actually going to be a map that contains two keys. One key is the value, and the other key is the minimum, right? The value is going to be presumably an integer, right? And the minimum is going to be an integer, right? Oops. Okay, so that's going to be our stack, is 0 more of these value minimum integers. And, okay, so peaker, when you peek, you're going to need to call the stack min, the peak, and the value. I guess we can call it peak and just do closure core.peak, I think. /peak. Okay. And then call value, right? The min is actually, interesting enough, going to be the same thing now. And min. Okay. And I think that's it for those guys, yeah. So anyway, now we do the peak, right? We got the stack man, which means what we wanted out of this guy was the minimum, because what we need to ask ourselves is, are we... Well, no, we don't need to ask ourselves anything. But because we're going to do it every time. There is no conditional part to this logic. We're just going to say conj, or with meta. No, with meta. We're going to say conj onto stack min. We're going to conj the value, which is a map that contains a value of v and contains a minimum of the min of minimum and v, right? So yeah, from the last minimum, right? We're taking the min with the last minimum plus the new value, right? And that should be the new minimum. And I think that's basically it. Maybe this way, yeah. And that's push. And pop is the opposite. Well, no, it's going to just say... Pop is actually just pop, I think. And we're going to have to do the closure core thing again as well, because we've overwritten it. Closure core pop on stack min. I think that's actually it for that. Alright, well that's something. I'm going to put all this stuff, this commented code out at the bottom. Down a rabbit hole. Yeah. And okay. And then let's do some tests. And okay, so test. Okay. Yeah, I don't really know. So let's build a stack. You know, S. All right, and then from the stack we can do things like. Like test slash is, I don't know, does, I kind of feel that, okay, I guess an easy one is the stack equal to the empty thing, right? That should definitely pass at this point. Yes, okay. Another one might be, does popping, or just popping onto the stack, you know, I don't know actually how to check if an exception is thrown. Closure, test, check, exception. Thrown, yeah. I think it's an assertion error, yeah. Thrown, assertion error. Let's see. If we try to pop the original stack, and yes, pop takes one argument, and it should. Oh, you know what? We don't actually. Yeah, you can't pop off an empty stack. Okay. Cool. All right, we're gonna get in there. Let's do the same thing for peak, min, and pop. Actually, all four of them actually have it. Wait a minute, somebody shouldn't have this. This guy shouldn't have this, but he will not be able to pull fudge. Well, we'll deal with that in a second, right? But at least peak, min, and pop should not be able to. And pop, yeah. Let's do just a little bit of check that exceptions are thrown on empty for. I'm not really sure exactly how to English-wise structure these things, but okay. It's actually also true of push, which should not be true. Ugh, gross. Alright. We could just put the whole thing on try catch. And then, like, if that happens, to just return a stack with a value v and a minimum of v. Okay. And what else? Okay, so let's try actually adding things to the stack. Right, so now we have a non-empty stack. And check non-empty stack functionality for. Alright. Okay, so like t slash is equal to 1 should be equal to the peak of the stack, right? The min of the stack should also be 1. And the pop of the stack should be the empty stack. Okay. Count not supported on this type, blah, blah, blah. Column 16, it says. Column 16, it says. All right, where are we? 17 to 16, yeah. Should be supported. Push. Oh, I think I misused it. No, okay, push, stack min. 1. Oops, what am I doing? Push, stack min. 1. What are we doing here? Parse. Push, stack min. 1. You're saying line 16. Something on line 16. Oh, line 33, column 16. I'm just a genius. Okay. Line 33. Okay, so it's from here. So line 33, column 16. Count not supported on this type. So line 33, this guy, goes to push, which goes to this guy, which goes to here, which goes to this guy. What's the issue? I don't, it sure seems like count should be supported on a stack. Count should be supported on a stack. You know, I did name this that. Actually, I kind of don't like that. Let's call this stack build. Well, I'll just, hopefully I haven't done that, something dumb. Okay, so it is probably an issue with this. Yes, okay, so push stack min, so let's just comment stuff out. Okay, so it's an issue with that. And what if we just return nil instead of this entirely? No, we just still have an issue. Huh. Is it the same issue? Line 34. Line 30. Body run, stack min, line 33, column 16. Next comes with type parse function plus body. I don't see what your problem is. All right. Whew, what is... Alright, comment this out. No, can't comment just that out. Doesn't even... No, you can actually. Now there shouldn't be an exception in here, but it should return a weird result. Okay, so it's something in here. Pretty sure it's this, but... Conj onto stack min. I cannot possibly see how that would be failing. Oh, I guess I could see if this is nil. This won't work, right? Oh, wait. Maybe it's just that this doesn't return a map. It just returns a value. Let's move on. Count not supported on this type. God damn it. Count not supported on this type. Alright, so it's something in here. I could just give it a value of like 2. Jeez, we're still failing. Cannot call min with 1 argument. Well, I don't know why you would be trying, since I'm calling with 2. Oh. You're clearly calling with 2 arguments, not 1 there. Line 34. First of all, you're not on line 34. Oh, okay, you are. Well, why is it saying line 34? Why isn't it saying something deeper than that? I don't get it. Why isn't it calling something deeper than... Why is it stopping right here at line 34? Cannot call min with 1 argument. Okay, I get your problem. I don't understand how you're calling min with 1 argument. Since I'm only calling min right... Oh. Gosh darn it. I didn't realize that. Ugh. I've used min. I should not name things the same thing so completely. Yeah. Okay, let's just fix this up. This is just crazy. Is empty doesn't exist. Peak does exist, so rather than overloading peak, let's just rather than overloading min, let's call stack min. Rather than overloading push does not exist, so that's fine. Pop does exist, so let's go stack pop. And now this guy is named, I'm going to name him the right thing, which is minimum stack. Or maybe at least stack with min. Okay. Alright, really, this guy just shouldn't have a name, because he's just the empty vector. Okay. Maybe that will clear up some of the things where I've accidentally overloaded them. line 31. Okay. Blankety blank. What the hell is that? Can now be cast to closure laying I persistent collection at line 31, column 16. Okay, so this was my previous... No, I do still have push. That was a mistake, actually. Oh, wait. Push stack 1. Line 32, column 11. Well, this is now a dumb test. There's no point in testing that. You know it's going to be true. Okay. God darn. All right. Can't pop empty vector. Okay. So it's actually a legal state exception and not a... But I think... Where am I popping? I'm popping on pop. But you should never be popping on empty vector because the assertion should have failed. How are you popping an empty vector? Who's popping an empty vector? Okay, you're trying to pop the 0 stack. It is the empty vector. Why didn't the assertion fail? Do I have to actually put... Huh. Is it... Huh. Are assertions disabled? I mean... Kind of seems like they are. What about pre and post? Nope, that doesn't fire either. Am I missing something obvious here? Why is... Oh, does pre go before this anyway? Closure pre and post. Pre and post go after the function argument, so that's probably just wrong. Okay, yeah. So I take the stack min, I take the count on it, and I ask if it's positive. Can't pop empty vector. Huh. So, kind of looks like assertions aren't being run. Babashka assertions. Babashka assertions. Okay, what about just try doing an assertion in general? So assert failed there. Why is assert not passing in my, or not running in my function? Okay, so pop should definitely fail here. I'm not clear. Oh, we can just throw an exception. When the stack is empty, then throw. I guess it's not really worth printing the stack, since if you know what the stack is going to be, it's going to be the empty stack. But I guess it is worth knowing. Maybe you're passing in something that you think is one thing and it's something completely different. But sure, let's not try calling throw empty. Peak should also be replaced by that. I guess strictly speaking, we could just reuse these. This is a dumb function though. Is empty stack. Okay. Okay. Sure you can. Well, you're right. Okay. Oh my gosh, I have so many errors in this one. Can't pop empty. Oh my god, come on. I'm literally... Can't pop empty vector. That must mean that I'm actually not... Yes, you're right. I'm a genius. Okay. You renamed it. Stack pop. Stack min. Stack peak. Okay. So that probably means the certs weren't working, and I was just being dumb. Okay. Do not rename core things. Okay, that is the take-home message here. Assert. Let's just see if we can get this to work. Stack min count is positive. Finally. Okay, that's just... Okay, we can get rid of this nonsense. Alright. So let's assert the other three. Okay. Let's just see if this works. Could now resolve simple stack like 38. Okay. Step 1. Step 1. Pop stack. Okay. That's cool, but what we really want to ask is if we build a big stack of... Actually, I just run. I think I just want to see the whole data structure. So, test the min functionality. T/is. I think we're going to need to actually build up a better stack first. All right, so let's take. Why am I only calling this guy push? That's just silly. Call him stack push. Look at stack push. Alright, reduce on stack push. We're going to start with the 0 stack. We're going to push on 1, 2, 3, 4, 5. So the bottom will contain 1 and the top will contain 5, which means everybody should have a minimum of 1. Right? Okay. So, and we can do the same thing for descending. DSC. 5, 4, 3, 2, 1. Okay. And so let's just say that the should be 1, 1, 1, 1, 1. If I call, not map, but there's another one called I think maybe iterate is what I'm looking for. Let's see. Yeah, okay. All right, so iterate of stack pops on let's say the stack ASC. Right, it should be all ones, right? Because the bottommost value is 1 and the topmost value is 5. So everybody has a min stack of 1. And then I don't actually want that, but for each of them I want to get the min, stack min on it. And although this returns infinite sequences, I'm only asking for 5 items, so but we do need to take 5 out of that. And we should be able to ask for a similar thing for descending, except it should... Wait a minute. That doesn't make any sense. Actually, this is the one I think that's always 1. Descending always has 1 as the min, but ascending has 1, 2, 3, 4, 5. Yeah. Let's just sanity check stack equal is It's got to be a number. Right? Just the min functionality. Okay. So it did not work on stack ascending or descending. Huh, that's interesting. So on stack push, I'm calling stack push with the first argument being the stack and the second argument being the value. And I'm pushing. Oh, you know what? We never pulled this out. It's kind of disconcerting how everything's still passing. I guess everything we texted up to that point didn't need a push. These are all zero stacks. Obviously, they don't have a push. These why did these pass with nothing in there? Well, because we weren't asking. We were asking for the. How come this one passed? Stack min, stack 1. It should have returned 1, not 2. Because I'm not clear. But 1, 2, 3, 4, 5. Not what I necessarily expected. All right, let's focus on one at a time then. Actually, let's do the other one. I feel like it should be simpler. So this should return all 1s because we're doing stack descending, which means we're going 5, 4, 3, 2, 1. So everybody's min should be 1. But it's not. Everyone's min is, in fact, 1, 2, 3, 4, 5. So something is definitely not working there. Almost feels like this is running every time. It's going to be too much noise, honestly. Alright, I don't quite see what's going on there, so I'm just going to call the identity on that. Just try to see what I see as the issue here. Yes, the only way I think this could be happening is if the assertion error is occurring, and oh, it's popping off the wrong end. How the hell is it doing that? Stack pop is popping off. Oh, you know what? I have my ascending and my descending backwards, I think. So if I'm ascending, the stack should actually contain 1, 2, 3, 4, 5. Which is what I said here. Yeah, I feel like that's what should happen. But instead it equals 5, 4, 3, 2, 1. How is this ending up at the end? Oh, because I did descending, yeah. Descending should be 5, 4, 3, 2, 1. Okay. And that's what we're seeing. 5 is the bottom, 4, 3, 2, 1. Okay, yeah, that's right. We're popping off the front of the stack. Blah. We're popping off the front of the stack, which is to say the rightmost element in this thing. So when we pop off 1, suddenly we should drop to 2. So when we're at our original, our stack min, for the first one, our stack min should be 1. For our second one, it should be 2. Wait, this isn't even the one that was wrong. I think maybe this one should be 1, 2, 3, 4, 5. But we are doing identity and not stack min. Okay. I think maybe this one should be 1 all the way across. Because your stack is ascending, which means the bottom of your stack contains 1 and the top contains 5. So everybody still has a min stack size of 1 at every point until the very end. Okay. Man, oh man. Okay, let's look at the code again. Empty is empty. Stack peak is stack peak. Stack min is stack min. Stack push is stack push. Stack pop is... I'm just reading. What am I even doing here? Stack peak, stack min. If you couldn't peak, that means that you were the empty stack. And so all we need to do is just return the stack with the minimum. About popping. If you couldn't, you do check that you're popping, and then we pop you. I guess we should check the peak functionality too, since so you should peak on all 1s, yeah. You should be peaking on descending, which means the thing I'm looking at I'm not quite sure, but let's just see if this is backwards or forwards. How did the same thing fail twice? So everybody's feeling on ascending. All right. So you're feeling on min. I feel that you should get all ones, but you're actually getting 4, 3, 2, 1, 1, which is weird. No, you know what? That actually makes some sense. I think they're actually right. Wait a minute. Are they right? Ugh. On mins, I thought they were supposed to be all ones, but a stack ascending contains 1, 2, 3, 4, 5, where 5 is at the top of the stack. So when you ask, no, I am pretty sure this should be all ones. Right? I mean, one of them has to be all ones. One of them has to be the minimum. Oh, you're not even doing the right one here. This is supposed to be... Okay, so now you're just feeling 1. 4, 3, 2, 1, 1. Okay, so the first one is indicative of what happens when you have all 5 holes in the stack. If you're descending, then you still have... Is that... Fuck, that just... If you're descending, then that means your numbers are getting smaller as you go deeper into the stack, right? If your numbers are getting smaller, then your numbers should be stable, right? It certainly feels like the descending one should be the one that... I said ascending here, but what I meant is I'm going to put 1 on the stack first, and then I'm going to put 2 on the stack, and then 3 on the stack, and then 4 on the stack, and then 5 on the stack. So it is... Yeah, it's the naming is making it confusing. The numbers are ascending, but this is actually descending. Right? Because if I put 1 first, and then second, and then third, and then fourth, and fifth on the stack, the stack is descending. So you actually need to reverse the stack order if you want to. But if I put 1 on the stack first, then 2, and then 3, and then 4, and then 5, then the stack is descending. I don't know. It depends on how you look at it. Do you look at the stack from the top down or from the... Yeah, I would look at the stack from the things I can pull off the stack. And if I can pull the values off the stack in descending order, then the stack is descending. Of course, people would probably disagree with that. Okay, so I think I'm slightly confused about... So this is ascending from the root, right? This is descending from the root. Okay. So I'm not sure if these are right yet, but at least they're less ambiguous. Okay. 1, 1, 1, 1, 1. So if we're ascending from the root, we're getting bigger from the root, then everybody, I feel, should have the same value, which should be the root value in terms of their min, right? Similarly, if we're ascending from the root, then when you pop things off, then it should be I'm just gonna run it. So the other one that's failing right now is min. They're claiming this weird result, which just seems totally not right. So that makes me think min is not working. And that's 11111 43211. Stack ASC from root. Alright, let's identity this one because in fact, let's just take one just to make it easier. So it contains a stack where, yeah, value 1. What the hell happened here? Okay, so this guy, successfully pushed the first value onto the stack. This guy seems to have taken the minimum of 2 and 1 and arrived at 1, which seems like a reasonable thing. This guy seems to have somehow arrived at 2. Arrived at 2, given an argument of 3 and looks like 1, right? So clearly he's taking the value and the value of this somehow. He's looking at the peak, and the peak returns the value, not the minimum. The peak returns the value, not the minimum. And so what we actually need to do, I think, is take the stack min. We need to pop one item off the stack min, right? And then we need to peek at that. And then we need to, that's it. Fudge. I thought that might happen. Yeah, you can't peek off things that... Are we sure that we want to actually pop something off the stack? No, I'm pushing onto the stack, so I want the last item. But it's just that I want the stack min, not the stack peak, I think. Which I named stack min and stack min very cleverly. Good lord, I'm having a lot of issues with namings here. Screw it. I'm just going to call this one stack. Call this one stack. I'm going to call this one stack. I'm going to call this one stack. And okay. And yeah, I don't need to peek it. I just need to stack min it. So that looks reasonable to me. Value 3, minimum 1, value 4, minimum 1, value 5, okay. Alright, so now let's just try calling the stack down. Well, it didn't work. Oops, I forgot to take one. Alright, well, you know, I think that's it, but I'm going to just read what the last hint is just to, whatever, you know. Number 78. Consider having each node know the minimum of its substacks. Yep, we figured that out. Okay. Boy, oh boy. That was a lot more complicated than I expected. What is the big mistakes we made here? So this ultimately was very simple, and it really isn't much different than the fundamental implementations use of vectors. This is actually all four of these are really simple. It really is just this one, you know. It was a little bit different, you know. And the key here was, wait a minute, you do know what the stack minimum is at every level in the stack, you know. You don't have to recalculate the stack because it doesn't change at every level of the stack, you know. That was the huge miss here, you know. And there's some valiant efforts to fix that problem sort of at runtime rather than as you compute them. But I think the big miss here was, hey, just record it as you're processing it, and then you don't have to re-record it dynamically as you're running through here. In some sense, it's, yeah, I don't know. It's obviously a memory versus processing trade-off kind of thing, right? I mean, we're literally recording the minimum for every stack. For every element of the stack. But it's obviously the right solution. I should have thought of that. I think the thing I missed that was maybe the hint is they say you can do it all in O in one time, you know, and yeah, it's interesting. I hit upon the first hint was that I think I got sidetracked into thinking, oh, O of 1, they mean amortized time, so there must be some way to amortize this thing such that it's on average O of 1 time. But actually, they literally mean O of 1 time, non-amortized, but just O of 1, in that you calculated it based just on yourself plus the previous value, you know, and yeah, I think that was the biggest miss there was there. Obviously, spent a huge amount of time on that. I'm going to take a little bit of a break. Yep, that's it. Okay. Stage.